Okay, hello everyone. So by now I think everyone here has heard or used an LLM before. Obviously, all of us have. OpenAI, Claude, Llama. But for most people, they stay these black boxes and you don't really know what's going on inside of them. You just give it a prompt and it produces an answer. In this presentation, we're going to discuss how exactly those large language models produce output, and we're going to do it from a perspective of a single neuron in the neural network.
Consider just the length of this presentation, hypothetically, that you are a neuron. You're a simple linear function that just takes in input and provides an output. Your model of the world is naive, to say the least, but at least you can map simple linear relationships.
Yes, but however, you're a part of something bigger. You're a part of society. And this society is called a multi-layer perceptron, or MLP. So, in this way, you have a goal. You have a common goal. And the notice somewhere here at the end. And then you're all trying to collectively achieve it. Hence, what you do is you take some input produced by the previous layers or your previous workers, like in a B movie. Then, second one is you determine the underlying patterns in that data produced by your friends. And lastly, you try to reinterpret that data and pass it on to the next workers, so that collectively you'll take one step closer to achieving the stated goal.
Now, as you saw in the diagram, you know how a lot of people vying for your attention. You now need to decide how much you should value their opinion, and this is done through the weight. You can then shape this way of thinking with a bias that just adds as a simple addition or subtraction to the way you're thinking. This way you can change it slightly if you are off.
Yes. So for now, because you only have weights and biases, your total function is a linear function. Hence, given a wide set of points in higher dimension spaces, you cannot fit your line of best fit, your basically ways of thinking. You cannot shape it around the presented data well. Hence, you need to introduce some non-linearity. In humans, it can be thought as having hobbies. Say you play guitar. You become a deeper person. You connect to more people who maybe also play guitar or any kind of music. So you become this shaped personality and become a deeper person. So some of the functions that do this for neurons are sigmoid and tanh. So all you do is you collect the chunks of those nonlinear functions, and then you shape the final output to be a function consisting of them. And it can be scaled to any dimension. It scales to, I'm pretty sure, n-1 dimensions, where n is the number of nonlinear functions.
Now, you're very confident with your very complicated relationships, but sometimes confidence can be a problem. When you decide web dev isn't that good, you need someone to tell you, but wait, consider React. It's with this objective function called a loss function that will find the difference between your prediction and the actual output you give and tell you how much you're wrong. Obviously, the lower value the better, which is called the loss, and you want to lose out as little as possible.
So okay, this brings us onto the step of learning. Here, let's say you have a task at hand, but you have no idea how to complete it. Hence, you do what is naive to humans. You try and try and try. And by trying different approaches, you upload your success, creating in this, a graph that looks something like this. It usually, a function that has set boundaries and is continuous on all of it, has a defined minima or maxima. So hence, you try to find such a minima to reduce your loss or the number of mistakes you make in completing such a problem. So what you do, after graphing the loss against your approaches or initializations of weights and biases, also known as parameters, you find the grading of the slope. And it can be thought of as an importance of the lesson. So the further away you are from a minima, the larger of a step you need to take. And then you scale it by a learning rate, which is basically the intensity or the effort you put in. Because you might think, oh, maybe I should just take a tiny, tiny step and not overdo it. But sometimes you need the larger steps to converge to the minima faster. To bring this idea to a larger network, so MLP. MLPs are usually structured as, again, combinations of functions. Hence, it can be represented as a computation graph. So for each node in the computation graph, you find a partial derivative of the current parameters with respect to the final output to find how important and how it is and how much it informs the final output. Hence, you perform gradient descent on the partial derivatives, to scale the weights and biases and other parameters to basically learn.
Mhm. But now you need to think about longer problems. You're no longer solving, okay, if you give me a hat, what color is it? You're now thinking, okay, solve this entire equation from start to finish. So what you'll do is as you progress through the input, you'll put the solution that you have at the current moment back into your model. This way, you're actually considering past decisions you've made. But say you do an all-nighter, you think for long and long and long, you'll burn out. If you've ever multiplied a number smaller than 1 lots and lots of times, you'll eventually hit 0. You need to try and avoid that. And the way to do this is through long-term memory. Now you have a stream of long-term memory going above and short-term memory in the bottom, and this is called a long short-term memory unit. This way you think in parallel, so say you are, I don't know, playing Minecraft for 2 hours. You don't want that to replace cosine rule in your long-term memory. So usually the memory will be judged by a gate that will decide how much of that memory to pass through.
Now, having discussed recurring structures, we will move on to language processing. Computer, being an artificial structure, it cannot understand human language. Hence, we need to wait to represent natural language in a way the computer can understand. First, an English language alone, the English language alone, contains 170,000 words. Hence, we need to wait to compress it, to avoid using too much unnecessary contexts and words. This is called tokenization. What you do is you split a sentence given semantic contexts of each subword, and then you learn how to do that efficiently and in a way that compresses a given vocabulary the best. Then you do something that is called word embedding, or embedding words in a vector space given their relevance. So, as presented here, words warm and hot are really similar semantically. Hence, you place them really close in this simple two-dimensional representation. And then cold it's the opposite, complete opposite. So you place it far, far away. Hence, you create, for each word, you can create a vector embedding that basically decides where in the space of meaning each word is, or token. And then, consider the sentence, I ate pizza. It is opposite to saying pizza ate I. You don't want that to happen. So you introduce the notion of positional encoding. Here I've labeled each token by number. And then in this diagram, the following diagram, you assign each one of those tokens a unique identifier comprising periodic functions of different periods. And then you take the x coordinate and basically combine all of those values, intersections, into another vector. And it is usually the same dimension as the word embedding. Hence, to create the final embedding, you just add the two up.
Okay. So finally, you can understand language. The inner neuron within you rejoices. To celebrate, you decide to go to Spain for vacation. You hear what they say, you encode it or embed it, but you compare the numbers and realize they don't make any sense to you. And this is why you need a shared context. When you get English and Spanish, you need them to share a vector space so that you can understand both at the same time.
So now, we introduce a encoder-decoder network, basically. So what it does, say I only know English, and my friend only knows Spanish, and I want to say, I am walking here. You can say it as, I am walking here, or there. And then, I tie that sign of representation to English language. And so does my friend, but he doesn't do it to English, he does it towards Spanish. Hence, when I give him a sentence or a sign, I go there, he thinks I, so it's going to be a language for I in Spanish, then go and there in Spanish. So hence, you sequentially basically compress the knowledge into a shared context, and then the recipient or your friend will decode that meaning of that sentence in a language they will understand.
But now you need to decide your priorities. You don't care that much about the ands and the thers and the I's. You need to decide the actual information you want to get from the query you provide. This is where attention comes in. you will find the cosine similarity between each key and value. This way, you can judge how important something actually is so that you don't waste computation by passing through unnecessary values. And it is finally in the end where all of these techniques gather, where you decide, okay, I don't really need to judge everything. I can just decide how much I value everything with attention and cosine similarity, and do this a lot of times in parallel to then converge to a solution.
By the way, just to note, this diagram is the one presented in the Attention is All You Need paper, which is the original paper they used to implement OpenAI's ChatGPT. So, final stage. You finish your degree. You think you know everything, and yet you need to learn to apply your knowledge. When you go to a corporate world, you'll have to learn a specific way of talking, performing, collaborating with your co-workers, or just using your knowledge in production. Similar to this, large language models are curated because at the end of their first stage of their training, they just take an input and provide an unsupervised output. Hence, you need to supervise it, exclude prohibited words. You need to make it act as a useful assistant, and you do that by providing some private data and finishing. So basically adding some training on top of the one that has been completed. And that is how you create a large language model that is used in production.